we have been discussing about the photochemical named reaction. We have already discussed few named reactions. Now the next reaction is Bergman cyclization. This is a very important reaction in which we start with an open chain system and containing two acetylene bond and one alkene bond, and we construct the cyclic system, that is the aromatic system. This reaction allows the construction of substituted arenes. So it is possible to construct or to synthesize the aromatic compound with the different substituents, and through the reaction can be carried out either in thermal condition or photochemical cycloaromatization. Of course, open chain is going to give a cyclic system, and that is an aromatic system. The starting material is enediene and the reaction is takes place in the presence of a proton donor such as 1,4-cyclohexadienone. So these are the the conditions. We start with the enediene. So for example, it is like this: one acetylene bond, two acetylene bonds, and with one ethylene bond. So this is you can have a different substituent, and the reaction can be carried out either in thermal or photochemical. The another important condition is we need a very strong hydrogen proton donor, and that is 1,4-cyclohexadiene. That is also very important because this also gets this aromatic. So the side product in this one is cyclohexadiene. 1,4-cyclohexadiene is converted to the benzene ring. The most cyclations have a high activation energy. These reactions have higher, and that's why we need a very high temperature, such as around 200 degrees centigrade. 1,4-benzene diradical is formed as one of the intermediate, which is highly reactive and reacts with proton donor to give the corresponding arene. So these are few conditions. Number one is it can be carried out both in thermal as well as photochemical. We need a proton donor. The reaction has a high activation energy. That's why reaction takes place at high temperature. The diradical 1,4-benzene diol is the intermediate, which is highly reactive, reacts with proton donor such as 1,4-diene to give this. The overall reaction can be represented as shown over here. This is the starting material. The compound is open chain with one acetylene bond, second acetylene bond, and one ethylene bond. We can have a substituent R, and that's why. So under thermal condition or photochemical, 1CHD is the 1,4-dihydro 1,4-cyclohexadiene. 1,4-CHD cyclohexadiene. 1,4-cyclohexadiene is the proton donor, and this is the product. So you can see we start with an open chain, and then we end up with a cyclic, and that too is an aromatic system. We can have a different substituent R here. So it is you can see it is an extremely important reaction because we are synthesizing aromatic system, different types of arene, and it has a lot of application. The mechanism involved in this reaction is as shown over here. So this is under thermal or photochemical reaction that these two acetylene bonds can undergo concerted cyclization to give a 1,4-diradical, to give a cyclic 1,4-diradical, and that is what is mentioned here, that the 1,4-benzene diol is the 1,4-benzene diol is the main intermediate, which is highly reactive, and this reacts with CHD. The 1,4-cyclohexadiene is a proton donor. See, this one of the radical can abstract an hydrogen atom from this, and then it can once again generate a diradical here, and then one proton, of course, abstracting a proton, it gets this. So this is the, and then this diradical once again can this another radical can abstract another proton to give the fully aromatized product, and then of course the dihydro 1,4-dihydrobenzene is converted to benzene. So we start with one open chain, we start with a cyclic 1,4-diene as a proton donor, and then we end up with two cyclic system, and both are aromatic. 1,4-diene is converted to as a byproduct, as a benzene as a byproduct, and whereas the open chain system, the acetylenic compound can be converted to substituted diene. So you can see it is a this named reaction, as we can see, it is Bergman reaction. Bergman cyclization is extremely important because we are generating a cyclic aromatic system. We can have a different R substituent to give a variety of substituted arene and benzene as a side product. So we get both the products are aromatic, and so this is another important name reaction which is triggered by photochemical as well as thermal, in the presence of a very 1,4-cyclohexadiene as a donor, and we can see the simple step concerted stepwise reaction can be explained, can be visualized as shown over here. The first is the cyclization of two acetylene bonds to give a 1,4-diradical, and then this can abstract a hydrogen atom to give a these two products, and then this other radical can also abstract another radical to give the both aromatized products. So these are few reactions which we have come across. One, photophrise rearrangement, and then this is the another one. Of course, we have also discussed Barton reaction, and we also this is the I think fourth name, photochemical reaction. Now, as far as the reaction which we have discussed so far earlier is we have discussed the reaction of aromatic benzene ring. The benzene can undergo different cycloaddition reactions such as 1, 2, 1, 3, and 1, 4. We have already discussed and looked into the synthetic application of those reactions, and benzene can add in a 3 different fashion. The addition of the polynuclear aromatic hydrocarbons such as naphthalene. Naphthalene can act as where this 9, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. The 9 and 10 position is highly reactive in the case of naphthalene, in the case of anthracene, as far as the reaction, and it acts as a diene. So these two double bonds acts as a diene in the case of anthracene, and if we have a very good dienophile, so this is a very good dienophile. The acetylene is also called as a DMAD, acetylene dimethyl acetylene dicarboxylate. The two dimethyl carboxylate groups at both the acetylene carbon makes is highly reactive, this triple bond. So this acts as a very good dienophile, and then the two double bonds at the reaction takes place with the, so this acts in a 4+2 cycloaddition, or we call it as a de-Sardo reaction. Reaction is initiated by either by neat heating the two reactants under thermal condition, or refluxing in the high boiling liquid like toluene. So this is a very important the reaction of anthracene with the dienophile, where anthracene acts as a diene. The most reactive carbons are 9 and 10 position. So these two double bonds act as a diene, and this acts as a dienophile. So it can act in a concerted manner to give a the Diels order adduct. So this is a adduct. So these two benzene groups are as it is, and of course these are the two this is 9 position, this is 9 and this is 10, and then we have a acetylene bond comes as a 9-10 position as well. So this is the 4 plus 2 addition adduct of anthracene with DMAD. DMAD dimethyl acetylene carboxylate. Similar reaction of anthracene with other dienophile have also been reported in the literature. And then another important dienophile is the dibenzoyl. Dibenzoyl, this is CO. I'm sorry, this is a mistake. Dibenzoyl acetylene dicarbox, C double bond C, COC6H5, COC6H5. This is called dibenzoyl acetylene dicarboxylate. This is another very important dienophile because of the presence of two electron withdrawing groups, such as two benzoyl group at two ends of the acetylene, makes it a very good dienophile. As we have seen, acetylene X reacts with DMAD. Similarly, dibenzoyl acetylene also reacts with acetylene at 9 and 10 position in a similar fashion, 4 plus 2. So this acts as a diene with a dienophile to give this adduct. So this is the 9 position, this is the 10 position, and the two benzoyl groups are over here, and of course two benzyl groups. So it is the reaction takes place at 9 and 10 position and giving rise to a two benzoyl group. So this is another very good dienophile. And this dienophile, that is DBA, dibenzoyl acetylene, can be synthesized in the laboratory by a series of reactions, starting with a highly commercially available diacid, that is the fumaric acid. In the presence of PCl5 gives dibenzoyl ethylene, ethylene dichloride, diacetyl acid chloride, corresponding acid chloride. Fumaric acid on reaction with PCl5 give rise to corresponding acid chloride, and this in the presence of benzene undergo Friedel-Crafts reaction to give you dibenzoyl ethylene. Of course, it is going in all trans manner because it started with the trans ethylene. So fumaric acid reacts with PCl5, gives rise to corresponding acid chloride, reacts with benzene in a via Friedel-Crafts reaction to give dibenzoyl ethylene, and this undergoes bromination to give you 1,2-dibromo 1,2-dibenzoyl ethane. So this is a highly and then this in the presence of triethylamine as a base removes the two molecules of HBr. This goes like this, this goes like this, and then this goes like this. So this removes two molecules of HBr. One molecule gives a double bond, and another molecule of HBr gives to triple bond. So we get this dibenzoyl acetylene is considered to be a very good dienophile because of the presence of two benzoyl groups, can add in a similar fashion with acetylene at 9N position and may via Diels order reaction under thermal condition, go 4 plus 2 cycloaddition reaction as DMAD goes, which is well known, and a lot of reactions of DMAD has been reported in the literature. And whereas this dibenzoyl COC is not, this is COC6H5, and the sequence of reaction through which dibenzoyl acetylene, which can be prepared in the laboratory, is shown on this slide here as well. Now the reaction of anthracene with DBA has been done extensively, and which also adds in a similar fashion addition of acetylene to 9-10 position to give a similar adduct. Now we have since we are interested in photochemical reaction, we know that if you look at this, is the adduct of anthracene and adduct of anthracene with dibenzoyl acetylene. If you consider two double bonds, one double bond is second double bond separated by a methylene group is nicely set for the dipymethane rearrangement. By methane rearrangement can undergo either these two double bonds or these two double bonds can undergo dipymethane rearrangement to give the cyclopropyl derivative. So we can construct a 5. This is benzene ring. This 6 benzene ring is as it is. These two benzene rings are no change as it is. Only the rearrangement is taking place involving these two double bonds, generating a 3-membered ring, and of course is also called as the dipymethane rearrangement. And we have two benzoyl groups intact, is substituent, and this reaction, the photoreaction, the first of all with different substituent. So this is prepared by a monosubstituted anthracene with R. So this R with the different R of anthracene substitutes such as methyl, CHO group, O-methoxy, COCH3, chloro, OCOCH3, ethyl, CH2OH, and then tertiary butyl NO2. So electron withdrawing, electron donating, and with the other halogen chloro substituted, nitro substituted anthracene have been reacted with dibenzoyl acetylene, C double bond C, COC6H5, COC6H5 can also give rise to the corresponding the 4+2 under thermal condition for Diels-Harder reaction and 4+2 cycloaddition reaction has been carried out extensively by Professor George group at IIT Kanpur, and so we can see that a variety of anthracene substituted at 9th position. This is a 9th position, and then we have already seen that the 9-10 positions of anthracene is highly reactive, acts as a diene to give can give an adduct of 4+2 cycloaddition reaction, and of course this adduct has further photochemistry of this adduct has been studied, and then this is nicely set for dipymethane rearrangement, and then it gives the corresponding, it undergoes the dipymethane rearrangement to give the corresponding semi-bulvaline. Semi-bulvaline is a common name for this. This is a dibenzobarylene, and then so these phototransformation have been well established, well characterized by different techniques, and it has. So this anthracene is a monosubstituted anthracene, so there is no problem with the addition of this diene at 9-10 position because this is not very staggeringly crowded. But it has been found that if anthracene is disubstituted at 9 and 10 position, if we have a different R and R2 group at 9-10 position, due to the depending upon the bulk of the group R1 R2, if it is quite bulky, then due to the steric hindrance, it has been found that the not only so when R1 and R2 have different substituent as mentioned here, we get a mixture of two products. One is 9-10 added product, 9-10 added product, such as this one, as well as the due to the steric hindrance, 9-10 position is not active, whereas the other benzene ring double bond, other two double bonds of the benzene reacts as called a naphthobarylene. So these reactions have all. These were the another interesting result where if in the case of monosubstituted anthracene, it gives exclusively 9-10 added product, which on phototransformation leads to dipyrmethane rearrangement to give the corresponding photo product with the construction of a 3-membered ring with the 2 benzene rings attached to this tricyclic ring system, whereas 2 benzene rings and 2 benzoyl groups are already intact. On the other hand, when the 9-10 positions of anthracene are di-substituted, and we, depending upon the bulk of the substituent, the 9-10 positions, the anthracene doesn't react at 9-10 position, but it reacts at the terminal benzene ring acts in a 4+2 cycloaddition to give you naphthobarylene as shown over here. So we get 2 products, dibenzobarylene as well as naphthobarylene, depending upon the bulk of the substituent. In the case of di-substituted anthracene derivative, where it can gives a mixture of 2 products. As usual, these two once again set for dipyrmethane. This we have already seen the photochemistry of this dibenzobarylene, whereas naphthobarylene can also set for dipyrmethane rearrangement to give the corresponding cyclopropane ring diradical, and then it opens up to give the corresponding photo product. The photochemistry of this has and now the mechanism for the formation of this from the photochemistry of dibenzobarylene to semipulvinene is shown over here. This is the final product under photolytic condition. This is a starting material. This is the product. This is a product, and then you can see this is R1, R2 at 9-10 position. One group is at cyclopropane ring, whereas other group at the adjacent cyclopropane ring. So under photochemical condition, there is a so this double bond and this double bond can interact to give a diradical like this, or this double bond or this double bond can react. So there is a possibility of 2 intermediates because both way it is reacting. So give a diradical. If these two double bonds are reacting, we get a diradical. This one, if these 2 double bonds are reacting, we get a diradical like this. And now this will undergo ring closure to give the benzene ring, and then opening of this. If you open the newly constructed bond, you go back to starting material. So if you open the old bonds, we get another diradical, and this will combine to give this product. And same way is this. This opens up. This will aromatize to give benzene ring, and this is a new 1,3 diradical, and this will combine to give cyclopropane ring. So there is a possibility of R1 on cyclopropane ring. There is also possibility of R1 going to the adjacent cyclones. Both the pathways are available, are open, and then to give of course we get 2 products, this one as well as this one, and then so there is a possibility of this is the stepwise reaction where the highly dibenzobarylene is a highly strained system, and there have been a lot of effort to construct the strain system looking at the photochemistry, because due to strain it opens up, and this starting material is nicely set for the product. The structure of this photo product as well as the starting material is highly complex, and it has been well proved by beyond doubt by single crystal X-ray, and the few structures of the product are shown over here. This is the photo product of the mono-substituted anthracene derivative, this one. So when we have a R is equal to CH2OH, R is equal to when anthracene is CH2OH. So if we have a starting material like this, CH2OH is a anthracene. It acts with acetylene, gives rise to this R is equal to CH2OH, and then this under phototransformation give you CH2OH on the bridgehead carbons, and then the structure of this is well established by single crystal X-ray, and we can see that this is the 5-membered ring. There is another 5-membered ring. This is a 3-membered ring. This is this benzo group benzene ring, and then of course you have a benzoyl group C carbonyl, and then C6H5 is another carbonyl 6. So these two benzoyl groups are here. This benzene ring is here. This benzene ring is here. These 5 rings, and then CH2OH. This is a CH2OH. So this structure has been well confirmed by single crystal X-ray beyond doubt. There is no ambiguity in the formation of the product. So dibenzobarylene undergo dipymethane rearrangement to give you corresponding same bulbarine derivative, and it has been well established. This is not only the reaction, but still the reaction of the dibenzoyl, as we have seen that the dibenzoyl acetylene is a very good good dinophile, but it can also react with nucleophile, and then nucleophilic reaction of the acetylene has also been reported as shown here. We'll discuss this in more detail on the next turn. Thank you very much.